very early days. Marketing commercialization paths are not clear at this point, so we chose not to spend any money on branding or naming. We just kept the company name the way it was. That trademark is applied for, it's not granted yet. The idea here is to take an existing technology and to push it into untapped market segments and other conditions that we think might be viable market segments for this existing technology of waterline formation testing. I'll give you a kind of a brief idea of what that is. Typically, test tools are deployed into an oil well or a gas well on a wire line that has ability to put power down the hole, and then some data comes back up on telemetry. This can be done both in open and cased hole. The open hole example is pretty straightforward. The formation being exposed. In cased hole requires perforations and a straddle packer. So I just grabbed this off the internet. The idea is that once this area of the wellbore has been isolated hydraulically, that some fluid can be withdrawn or injected, and then that will cause a pressure drawdown profile. You can see, what can we see? Oop, that's not exactly what I wanted to do. The red one, eh? Okay. So these are millidarcy numbers for the formation. And they're not all the same. We have very good reservoir rock that will deliver well. We have tighter rock that won't deliver very well. In the good reservoir rock, the drawdown is small, and without pump of adequate capacity to extract a good flow rate, you don't get much drawdown, and the subsequent buildup has less information. Conversely, when you draw it down a long way in bad rock or poor permeability, the buildup can take a long time and kind of approaches asymptotically to P star, the normal formation pressure, and that can take a long time and ultimately have bad data. Okay, so what we're trying to do here is to build a pump that will have enough oomph to it to deal with good porous rock, and also one that will have at the same time the capacity to take a kid gloves approach and to withdraw small amounts of fluid. That's kind of the way that these low deliverability zones are being addressed today, to incrementally withdraw small amounts of fluid and to thereby limit the drawdown and kind of speed up the build-up process. Let's see. Okay, design constraints. Hydrostatic pressure is mud weight in the hole, how deep the hole is, and one design choice. There's constraints and there's choices. Constraints are there, and you can design, to address a certain segment of the market, overall segment of the market, by picking your poison when it comes to how much pressure you want to build this tool to withstand. Wellbore temperature, and that's how I got on to ACAMP. Semiconductors have inherent limitations, at least the standard designs do, where the gate temperature can only go so high, and then you get issues with leakage currents. Silicon and insulator technology is making some progressions, and ACAMP is doing some packaging things to mitigate the effects of temperature on electronics. And again, at the end of the day, you can pick your power availability. You can pick, what kind of market segment you want to address, and there's large entities in this market space as well, although not where we're targeting. And we've kind of figured that 175 degrees C for a rating is about what we can get to. There's not just limitations on electronics, but elastomers begin to degrade. You've got problems with pressure integrity. Actuators, tempered steel will only begin to get softened if you have service temperatures that are in excess of that tempering. Let's see. So one of the problems with conventional wireline is how much power you can get down the hole. And pumping is horsepower, and it's a function of cable length, conductor size, and some other things. Copper does change as it gets hotter, so you get this temperature change coefficient going on where resistivity goes up as the wireline heats up, and this comes from kind of the maximum power transmission theorem, where if you drop half your power in transmission, you get about half down hole. So what we're trying to do here, also, one of the things we wanted to do is to make this in a slim profile, a slim diameter. There's, to my knowledge, no solution that'll get into the smaller casing sizes. And at 3 3/8, which is kind of a standard design diameter for open hole tools anyways, you can get into all the 5-inch casings and some of the lighter weight 4.5s. Typically, these tools are like 5.5 OD, 4.5 OD, the conventional offering. So we want to get into the slim casing case tool market and kind of fill what we see as being an untapped market segment. Most of this case tool stuff is done on kind of mom and pop trucks. And they got the large integrated companies like the Schlumbergers and the Halliburtons of this world. 5 more? Okay, I'm gonna have to keep going here. Yeah, okay. So we're gonna build a case tool solution on model cable so we can get on the rolling stock on the trucks that are available today. Conventional design objectives, mostly data gathering, pressures, fluid samples, identification. They used heptacable or 7-conductor wireline. They use hydraulics, a lot of hydraulics. We want to get rid of that. And some of the technology advances that have come along since those first tools were designed. We've got lots of motor control things going on that are pretty good. It's permanent magnet synchronous motors. This one happens to be an Infineon product map for available components. They're not super high temperature, but they're not bad. We've got some advances in position control stuff. These ones are Atmotech Rotosyn variable reluctance resolvers that we can use for commutation and motor control. We've got some actuators that we like from SKF. We had a custom one of these made. And so the idea is to take all this kind of technology and build a downhole pump that kind of minimizes the loss of power. There's some scarce supply down there. We want a direct drive planetary gear to get rid of the hydraulic losses from conventional hydraulic actuated downhole pumps, and also give us very good position control so we can have withdraw small amounts of fluid if that's what the situation calls for. We got a kind of a unique construction that should simplify assembly and make the whole thing go together, which is kind of a real design problem in slim packaging. Okay. Yeah, so the pump should be able to go high and hard or slow and have fine control for these conditions. Yeah, so then one of the things that we may be able to do, and we hope to be able to do, is to attack this low permeability problem by mini frac or mini stimulation to try and take the service offering beyond simply data gathering and actually do something in the hole. 2 minutes. Yeah. Okay, so there's efficiency of the downhole screw. There's the model of the pump section we bench tested. That's Yaskawa server drive there for the bench test. There it is in the lab. And there it is running. You can see over here, you got a piece of 1/8" sludge lock tube, and it's kind of like a pressure washer, really. Maybe 1,500 pounds in the gauge. And so that's the first run. That seemed to be okay. Right now we're putting the motor in there. We got a custom design going on. I'll put this up because it's a lot of choice there. And some housings. I didn't want to put too much sections in there. Things that when I wanted to do this, I didn't want too much in there. Some sections are going to be published probably in May when the patent gets published. Those are the housings. And ultimately we want to be able to get some fluid out of the well. And that's a model we have of some flow rates quite a bit higher in cubic meters per day than some of the existing tools. I think I'm out of time. Thanks for having me here.